Deep under the border between France and Switzerland, there is a machine built to make emptiness violent. It does not look like a doorway to a black hole. Most of it is hidden from the sky, buried in a circular tunnel so large that towns sit above it without feeling its shape. Inside that ring, protons are stripped down to their bare charge and driven almost to the speed of light, guided by magnets colder than interstellar space, until two beams meet head-on inside detectors the size of buildings. For an instant too small for ordinary imagination, energy is compressed into a point where matter stops behaving like matter and becomes a spray of possibility. Then the debris flies outward. Tracks curve through silicon. Muons punch through layers of steel. Photons bloom inside crystals. Jets of particles appear where quarks and gluons tore themselves into something visible. The detector does not see a collision as a fireball. It sees evidence, fragments, angles, energies, missing momentum, a forensic map of an event that died almost as soon as it was born. Somewhere in that violence, physicists have searched for something almost mythic, signs that gravity, under the right conditions, might become strong at microscopic scales. In certain speculative models, if space has hidden extra dimensions, then the true strength of gravity could be different from what we experience in the wide, cold world. And if that were true, a collision at the Large Hadron Collider might briefly create an object so extreme that even light would have no route back out. A microscopic black hole. Not a cosmic monster, not a star-collapsing abyss, not a devourer of planets. Something incomprehensibly smaller, hotter, and shorter-lived. A black hole that would vanish almost instantly, if it existed at all, leaving behind a violent burst of particles like a final signature written into the detector. But the important thing is not that CERN found it. It did not. The official searches found no experimental evidence for microscopic black holes in those collision records. The machines waited. The detectors listened. The predicted patterns did not appear. The absence itself became part of the map, a boundary drawn around what certain theories could still claim. So the title is wrong if it is read literally. CERN has not found the missing ingredient inside black holes. It has not solved the oldest wound between gravity and quantum mechanics. It has not opened a tiny event horizon under Europe and watched the universe confess its secrets in a spray of particles. But there is a reason the title still pulls on the mind. Because black holes do seem to be missing something. Not matter. They have mass. Not gravity. They are gravity made almost absolute. Not darkness. Darkness is the least mysterious thing about them. The missing thing is stranger. It is information. Not information in the human sense. Not words, memory, meaning, or data stored on a machine. In physics, information is more severe than that. It is the exact distinction between one possible state of reality and another. It is the complete accounting of what something was. Every particle, every quantum state, every correlation, every hidden detail that makes this universe, and not a slightly different one. When a book burns, the story is gone for us. But physics does not simply say the information has vanished. The smoke, heat, ash, and radiation still carry the microscopic consequences of the burning. In principle, if some impossible intelligence could track every molecule and photon, the past would not be erased. It would be dispersed. It would be scrambled into a form too fine for us to read. That is ordinary destruction. A black hole threatens something deeper. Drop a book into a black hole, and the outside universe loses access to the book. Drop a planet, a star, a library, a civilization, the bones of a dead galaxy. From far away, the details appear to sink toward a boundary where signals slow, redden, and fade. What remains measurable from the outside is brutally simple: mass, electric charge, spin. The black hole does not seem to care whether it was made from hydrogen, iron, light, dust, or the collapsed archive of a million histories. It wears almost no memory. This was already unsettling, but it was not yet fatal. If the information stayed hidden inside forever, perhaps reality could keep its books behind the horizon. Perhaps nothing was destroyed. Perhaps the universe had simply built a vault. Then Hawking made the vault evaporate. Quantum theory near the event horizon suggests that black holes are not perfectly black. They radiate, extremely weakly for large black holes, almost unimaginably slowly, but not never. Over vast stretches of time, a black hole can lose mass. It can shrink, it can fade, and if nothing stops the process, it can disappear. That is where the floor drops. If a black hole forms from a precise quantum state, then evaporates into radiation that carries only thermal, featureless information, only the broad properties of heat, not the detailed structure of what fell in, then the universe has done something quantum mechanics says it should never do. It has taken many possible pasts and turned them into the same future. It has allowed distinction itself to die. The terror of the black hole is not that it crushes matter. Matter is crushed everywhere. Stars crush hydrogen into helium. Supernovae crush atomic nuclei into elements. Neutron stars crush matter until atoms lose their familiar shape. The universe has never promised comfort to matter.
But information is different.
Modern physics is built on the idea that, at the deepest level, the state of a system evolves according to rules that preserve enough structure for the past and future to remain connected. The motion can become chaotic. The information can become unreadable in practice. It can be scattered across radiation, hidden in correlations, diluted into heat. But it is not supposed to be annihilated. A black hole asks whether that confidence was naive. It asks whether the universe can take a fact, not a human fact, but a physical distinction, and remove it from existence. It asks whether the laws that work everywhere else become incomplete at the edge of an event horizon. It asks whether space and time, those familiar coordinates in which we place everything, are not fundamental enough to explain what must be preserved. That is why the CERN image matters, even without the discovery the title implies. Because in those collisions, physicists are not merely smashing particles. They are pressing reality into a corner. They are asking what happens when energy becomes dense enough that gravity should stop being background scenery and start entering the quantum conversation. They are not looking for spectacle. They are looking for failure, a pattern that says our current theories have reached their limit. No microscopic black hole has appeared in the detector, but the larger black holes in the sky already hold the question open. They sit at the edge of physics like perfect legal traps. General relativity says, here is a boundary beyond which escape is impossible. Quantum mechanics says, the bookkeeping of reality cannot simply end. Thermodynamics says, black holes have entropy, temperature, and heat. Hawking radiation says, the thing that cannot lose anything may slowly lose itself. Each statement is serious. Each comes from a theory that has earned trust. Together, they do not fit cleanly inside the human mind. The result is not a mystery in the cheap sense. It is not a gap where imagination can do whatever it wants. It is a disciplined contradiction, built from success. We did not arrive at the black hole information problem because our theories failed too early. We arrived there because they worked too well, too far, and finally began making demands on each other that no ordinary picture of reality could satisfy. A black hole is often described as a place where nothing can escape. That is not the deepest version. The deeper version is this. A black hole may be the place where the universe is forced to decide what nothing escapes even means. If information remains inside, what happens when the inside evaporates? If information comes out, how does it cross a boundary that was supposed to forbid return? If information is stored on the horizon, then what was the interior? If information is truly lost, then what becomes of the laws beneath every quantum process we have ever tested? The question is not whether black holes are powerful. Of course they are. The question is whether they are powerful enough to make reality forget. And that is the real missing thing. Not a particle in CERN's detectors, not a hidden substance behind the horizon, not some final object waiting at the center of collapse. The missing thing is the answer to a single, merciless demand. When something falls into darkness, does the universe still know exactly what it was? The terrifying part is not that black holes eat the world. It is that they may ask whether the world remembers itself. There is a kind of disappearance that feels final only because we are small. A page burns in a flame. The paper curls at the edge, darkens, and opens into orange light. Ink that once held a sentence breaks into heat, smoke, carbon, water vapor, invisible molecules moving too quickly for the eye. A moment later, the story is gone. The ashes do not remember the paragraph. So the mind reaches for an obvious word. Destroyed. It is a useful word. A broken cup is destroyed. A deleted file is destroyed. A body reduced to dust is destroyed. If no one can rebuild the cup, if no one can read the page, if no witness can restore the exact arrangement of what was lost, then for us, the thing is gone. But physics is colder than usefulness. At the level beneath ordinary perception, burning is not amnesia, it is transformation. The molecules in the paper do not pass into non-existence. Their bonds break, their atoms recombine, energy flows outward, photons leave the flame, air currents carry chemical traces away. The event becomes harder to reconstruct, not because reality stopped keeping track, but because the record has been scattered into too many places at once. The past has not vanished. It has diffused. This distinction is easy to miss because human memory is coarse. We remember shapes, names, faces, stories. We do not remember the exact motion of every molecule in a room. We are built to survive at a scale where approximation is mercy. A fallen glass becomes shards. A shattered window becomes a problem. The fine details sink beneath attention. Reality does not have that threshold. Or at least, quantum mechanics says it should not. The state of a physical system is not merely a rough description. It is the full mathematical specification of what can happen when the system is measured, how its possibilities interfere, how its parts are correlated. This state can evolve into forms that look random to us. It can become entangled with an environment so enormous that recovery becomes practically absurd. But the basic rule remains severe. Evolution should preserve distinctions. Different beginnings should not become exactly the same ending. This is why ordinary destruction is not enough to frighten physics. Take a glass vase and drop it on stone. To a person, the vase has been ruined. To physics, the event is extravagant but lawful. The arrangement of atoms has changed. Sound carries energy through air. Heat appears where surfaces crack and slide. Tiny fragments fly in different directions. The original form is lost as a human object, but the microscopic consequences still contain a trace of how the fall happened. The world has written the memory into chaos. Chaos is not erasure. Chaos is precision beyond reach. This is what entropy so often hides from intuition. Entropy is commonly described as disorder, and the word is dangerously soft. Disorder sounds like messiness. In physics, entropy is closer to the number of microscopic ways a system can look the same at the scale we care about. A smooth cup of coffee cooling on a desk seems simple. Beneath that simplicity, molecules trade energy in a swarm of arrangements too vast to imagine. The coffee forgets nothing, because coffee was never remembering. The point is stricter. The detailed physical state is still carried by the whole system and its surroundings. Heat moves into the air. Infrared photons leave the surface. Microscopic collisions continue inside the cup. All of it participates in a record no person could gather, no machine could realistically reverse, but not, in principle, a record that has become nothing. This is the false comfort we bring to black holes. We think we know what loss means because we live among broken things. Bodies age, buildings decay, hard drives fail, civilizations leave fragments under soil and water. So when we hear that a black hole destroys something, the idea feels like an extreme version of a familiar fact. But it is not familiar. It is alien. Because the black hole is not merely a violent environment where matter changes form. A star can tear matter apart. A supernova can forge elements. A neutron star can crush atoms until ordinary chemistry has no meaning. Those are severe transformations, but they do not automatically violate physics. They rearrange, they scatter, they compress, they radiate. The ledger becomes difficult, perhaps impossible for us, but it is not obviously burned out of reality. A black hole introduces a different kind of boundary. Not a boundary of difficulty. A boundary of access. Outside the event horizon, the universe remains connected to you by signals. Light can arrive. Gravity can be measured. Information can move from place to place, limited by the speed of light but not severed entirely. Inside the horizon, every future-directed path points deeper inward. Signals do not merely struggle to escape. Escape is no longer in the causal future. The horizon does not make recovery hard in the way smoke makes reconstruction hard. It changes what can ever be communicated back to the outside. That is why the ordinary language of destruction becomes dangerous. If a book burns in your hand, the information is scrambled into the world around you. If a book crosses an event horizon, the outside world appears to lose access to its details. Still, this alone might not break physics. Perhaps the record remains inside. Perhaps the black hole interior is a sealed archive, unreachable but not non-existent. That would be strange, but not yet catastrophic. The catastrophe begins only when the black hole is allowed to die. Because if the horizon hides the information, and Hawking radiation drains away the mass, and the radiation carries no detailed imprint of what fell in, then the sealed archive does not merely become unreadable, it disappears with the vault. The difference between one history and another is no longer scattered. It is no longer hidden. It is gone from the final state. This is what ordinary intuition cannot absorb. We are comfortable with loss because we confuse our limitations with the universe's limits. We call a page destroyed when we cannot read it. We call a memory lost when no brain holds it. We call a structure ruined when no one can rebuild it. But physics has always been more exacting than human grief. It does not ask whether something can be recovered by us. It asks whether the distinction still exists in the total state of the world. Black holes force that question into its harshest form. They take the human experience of watching things vanish beyond repair and expose the hidden assumption beneath it. We assumed irreversibility was absolute because our lives are irreversible. We assumed loss was fundamental because everything we love can be lost. But at the deepest level we know how to test, nature seems less sentimental and more severe. It allows scrambling, decay, heat, ashes, silence, and ruin. What it may not allow is forgetting. Fire hides information in smoke. Time hides information in complexity. Entropy hides information in numbers too large for any hand to gather. A black hole may hide information behind the architecture of causality itself. And once that possibility exists, the old comfort collapses. The comfort was never that things do not disappear. Of course they do. The comfort was that disappearance was only local, only practical, only a failure of our reach. The deeper laws, we thought, still held the pattern somewhere. The black hole asks whether somewhere is enough. Disorder is not amnesia. It is memory written too finely for us to read. But an evaporating black hole seems to threaten something worse than disorder. It threatens a universe in which the writing itself may be gone. A black hole does not need a surface to become absolute. This is where the mind usually goes wrong. It imagines the event horizon as if it were the skin of an object, a dark shell wrapped around the collapsed mass, a physical edge where the universe changes texture. It imagines a boundary one could almost touch, a place where a falling astronaut would see some final line approaching, some black membrane stretched across the future. But the horizon is not a wall. There is no metal there, no glass, no hard edge, no local sign saying the outside is ended. For a large enough black hole, someone falling through the event horizon might feel nothing special at the crossing itself. No sudden impact, no flash, no cosmic alarm. The body would pass through a mathematical boundary while the heart continued beating, while instruments still worked, while a wristwatch still moved 1 second at a time. That is the first cruelty of the horizon. It does not announce itself to the person who crosses it. It announces itself to the rest of the universe. From far away, the falling object seems to slow near the horizon. Its light stretches toward red, then deeper red, then wavelengths too long and faint to follow. Signals arrive more weakly, more slowly, as though the object is being pressed into an endless last moment. The outside observer never sees the crossing in the ordinary sense. The fall becomes a fading inscription on the edge of darkness. But for the falling object, there is no endless freezing. There is motion. There is inward time. There is the local feeling that physics continues. This split between viewpoints is not a trick of perception. It is a warning that the black hole does not fit inside the simple geometry our intuition uses for the world. We are used to places being shared. A door is a door for both sides. A wall is a wall for whoever approaches it. A border can be crossed, guarded, measured, drawn on a map. The event horizon is stranger. It is not defined by what is happening at that exact location, in the same way a cliff is defined by a drop. It is defined by the causal structure of space-time. It is a boundary made from futures. Outside the horizon, there are paths that lead outward. A rocket can burn fuel. A light beam can climb away. A message can move from one region to another. Not every escape is easy, but escape still belongs to the menu of possible futures. Inside the horizon, that menu has changed. Every future-directed path leads inward, not because the traveler has chosen poorly, not because the engine is too weak, not because the black hole pulls harder than courage can resist. The word outward has lost its usual meaning. The direction that once led away from the center no longer leads into the future. The singularity, or at least the region where classical general relativity predicts its own breakdown, lies ahead the way tomorrow lies ahead. This is why escape velocity is only a partial metaphor. People often say a black hole is an object whose escape velocity exceeds the speed of light. That image has use, but it quietly smuggles in the wrong picture. A rocket sitting on a surface, trying to climb out of a gravitational well. A real event horizon is not just a place where speed is insufficient. It is a place where the structure of cause and effect has tilted so completely that all future roads point deeper in.
A swimmer in a river can fight a current.
If the current is too fast, the swimmer is carried downstream. But inside a horizon, the analogy has to become harsher. The river is not merely flowing inward through space. Space and time themselves have changed their roles, so that inward motion is no longer a destination one might avoid. It is woven into the future. The horizon is not a wall in space. It is a decision made by time. And this is where information begins to feel trapped in a new way. A burned page can send its traces outward into the room. Smoke rises, heat leaves, light carries away evidence. Even if no one can reconstruct the sentence, the world has been touched by the event. The record leaks everywhere. A page falling through the event horizon does something different. Before it crosses, light from the page can still climb outward. The outside universe can still receive some trace. After it crosses, no signal from the page can reach back. The page may still exist in its own local future. Its atoms may continue to move. Its quantum state may still participate in some deeper description. But for the outside world, the causal door has shut. This is not ordinary privacy. It is not a box with a lid. A locked box still sits in your room. You can weigh it, shake it, cut it open, wait for sound to emerge. The information inside is inconveniently hidden, not causally exiled. An event horizon is different. It is a boundary beyond which future-directed communication to the outside is impossible. That word, impossible, must be handled carefully. It does not mean difficult for current technology. It does not mean impossible because humans are weak. It means impossible within the space-time structure described by general relativity. No better antenna solves it. No faster engine solves it. No clever signal solves it, because the very notion of a future path back outward is gone. This is what makes the black hole so clean and so merciless. Most physical systems are messy. They leak, they vibrate, they radiate details. They have surfaces with complicated chemistry, interiors with turbulence, magnetic fields, cracks, histories. A planet carries scars, a star carries spectra, a cloud carries structure. Even when nature is violent, it often leaves fingerprints. A classical black hole is almost offensively simple. From the outside, it can be described by only a few quantities: mass, electric charge, and angular momentum. That brutal simplicity became known through the idea that black holes have no hair. Not literally hair, but distinguishing features. The collapsed object may have formed from an enormous range of possible histories, but the final exterior description seems to remember almost none of them. A star of hydrogen, a star of heavier elements, a swarm of particles, a collapsing shell of radiation. Given the same mass, charge, and spin, the exterior black hole looks the same. This is not yet the paradox, but it is the first pressure point. If the outside world can only measure a few properties, then where did the rest of the detail go? General relativity can answer, for a while. It went inside. The information is not destroyed. It is simply hidden behind a horizon, carried inward where outside observers cannot receive it. That answer feels stable until the black hole is treated as permanent. If the horizon remains forever, then perhaps the universe has not erased anything. It has only partitioned itself. There is an outside record and an inside record, forever separated. Strange, yes. Disturbing, yes. But perhaps not a violation of the deep accounting. The event horizon would be the ultimate archive door. Closed, but not empty. Yet the deeper we look, the less this door behaves like a comforting archive. It is too smooth, too simple, too indifferent. It accepts detailed things and presents the outside with almost no detail in return. It swallows complexity and answers with geometry. Mass, charge, spin. That is the language the exterior hears. The rest falls silent. And silence is tolerable only if something, somewhere, still speaks. General relativity can keep that hope alive by placing the missing details inside. But the horizon has already changed the emotional shape of the problem. It has turned information loss from a practical difficulty into a causal wound. It has shown that a black hole does not merely scramble the record like fire. It can remove the record from the communicable universe. The first crack in the obvious is not that black holes are strong. It is that they are lawful. They do not need chaos to threaten us. They do not need noise, turbulence, or visible violence. Their danger is clean. A horizon can be perfectly smooth and still divide reality more completely than any material barrier ever could. That is why the next step is so devastating. If black holes only hid information forever, the universe might survive the wound by never reopening it. But quantum theory does not let the horizon remain silent. It makes the black hole leak. The horizon was supposed to be silent. That was its terrible elegance, a boundary without a surface, a place where the outside universe could still measure mass, charge, and spin, but nothing more intimate, a place where the details of fallen matter became unreachable, sealed behind the geometry of no return. In the old picture, the black hole was almost perfect because it was almost mute. Then quantum theory placed a restlessness around the edge. Not a glow you could see with human eyes near a stellar black hole, not a dramatic halo of fire, not the violent disk of matter that may whirl outside a black hole before falling in. That disk can blaze across space, but it is not the black hole itself shining. It is doomed material heating, colliding, spiraling inward. The black hole, classically, remains dark. The deeper radiation is quieter. It comes from the fact that what we call empty space is not truly empty. In quantum field theory, emptiness is not a dead stage waiting for particles to appear. It is the lowest energy condition of fields that still possess fluctuations, uncertainty, and structure. Even in a vacuum, the fields are there. They do not vanish merely because no particle is being counted. Near an event horizon, that vacuum becomes difficult to define in the old, comfortable way. A black hole divides space-time into regions with different futures. What counts as empty for one observer does not have to count as empty for another. The horizon bends the relationship between time, energy, and observation until the vacuum itself becomes observer-dependent. Out of this severe mathematics came Hawking's result. Black holes should emit radiation with a temperature. A temperature. That word should feel almost indecent. Temperature belongs to kettles, stars, furnaces, bodies, dust warmed by sunlight. Temperature is the language of restless matter. To give a black hole a temperature is to say it is not merely a geometric trap. It is a thermodynamic object. It participates in heat. It has entropy. It can lose energy. It can change. The thing that nothing could escape from begins, in the quantum description, to leak. The leakage is not like steam escaping a pipe. No particle climbs out from deep inside the horizon after deciding to disobey relativity. That picture is tempting, but too simple. Hawking radiation is better understood as a global effect of quantum fields in curved spacetime. The black hole's presence changes how the field modes are related between the far past and the far future. What begins as vacuum can be perceived at infinity as a bath of particles. The language is abstract because the process is not built for human imagery. Still, the consequence is physical. The black hole radiates. For an astrophysical black hole, this radiation is unbelievably cold. A black hole with the mass of the Sun would have a temperature far below the cosmic microwave background, colder than the lingering afterglow of the early universe. It would absorb more ambient radiation than it emits. It would not visibly shrink while stars still burn and galaxies still turn. But the formula is patient. As a black hole loses mass, its temperature rises. Smaller black holes are hotter. If a black hole could become small enough, it would radiate more intensely. In the far future, long after ordinary structures have faded, evaporation could become the final act of a black hole's life. The important part is not the heat itself. The important part is that the perfect prison is no longer permanent. Before Hawking, one could imagine the event horizon as a final storage place. Information crosses inward, the outside loses access. But perhaps the information is still there, inside, forever. The black hole becomes a locked archive at the end of causality. Unreachable, yes, but not necessarily destructive. Hawking radiation changes the emotional geometry of that hope. Because a radiating black hole has a lifetime. Not a lifetime like an animal or a star. For large black holes, the timescales are so enormous, they make ordinary cosmic history feel brief. But finite still matters. If the black hole emits radiation and loses energy, and if nothing prevents the process from continuing, the black hole can eventually evaporate away. The archive does not simply remain closed. The archive dissolves. Then the question becomes merciless. What happened to the records inside? At first, the radiation appears to make the problem worse, not better. Hawking's calculation suggests that the radiation is thermal. Thermal radiation is described by temperature. It has statistical character. It does not obviously carry the detailed microscopic portrait of every object that entered the black hole. Whether the black hole formed from a collapsing star, a shell of light, or some exquisitely arranged quantum system, the late radiation seems governed mainly by the black hole's few external properties. Mass, charge, spin. The same thin vocabulary returns. This is why the black hole's whisper is so disturbing. It is not silent, but it may not be articulate. It speaks in heat, it sends out quanta, it fades. Yet the speech appears too generic to describe the life it consumed. A black hole made from a library and a black hole made from dust could, if their exterior properties match, radiate in ways that seem indistinguishable. The universe would not merely hide the difference. It would wash the difference into sameness. That is the wound. To see why, imagine a locked room filled with detailed records. The door closes. You cannot enter. For a while, you may still believe the records exist. They are unavailable, but not gone. Then, smoke begins to drift from under the door. Slowly, over centuries, the room shrinks. Its walls thin. Its mass decreases. Eventually, there is no room, only smoke. You gather every last particle of smoke and ash, expecting the records to be encoded there somehow. But the smoke only tells you the room had a temperature. That is the horror Hawking introduced into black hole physics. Not violence, not darkness, not even death. Generic aftermath. A final state too poor to account for the richness of the beginning. The classical black hole threatened communication. The quantum black hole threatens distinction. It does not merely place information somewhere unreachable. It seems to transform many detailed histories into the same featureless thermal end. If true, this would not be ordinary ignorance. It would be a breakdown in the idea that the future remains connected to the past by reversible law. This is why Hawking radiation became more than a prediction about black holes. It became a blade placed between the two great languages of modern physics. General relativity gave us the horizon, a causal boundary from which no signal returns. Quantum field theory gave us radiation, a slow leak that carries energy away. Thermodynamics gave black holes entropy and temperature. Quantum mechanics demanded that information must not be destroyed. Each piece was powerful. Each piece had reason behind it. Together, they formed a machine that seemed to grind information out of existence. That is a very specific kind of crisis. It is not the crisis of ignorance before a mystery. It is the crisis of knowing too much in incompatible ways. The theories do not fail by becoming vague. They fail by becoming precise and then refusing to agree on what precision requires. The black hole does not stay silent. It whispers itself away. And once it begins to whisper, the old refuge disappears. You can no longer say the information is safely hidden inside forever. Forever has been punctured. The horizon still prevents escape, but the black hole itself is losing mass. The outside universe receives radiation, faint and cold and patient. The interior, if the old picture holds, carries the details, but the exterior sees the black hole shrinking. The ledger is being closed, while the entries remain locked inside. Something has to give. Either the radiation is not as featureless as it first appears, or the horizon is not as absolute as classical relativity suggests, or information can be lost, and quantum mechanics must be altered, or space and time themselves are not fundamental enough to hold the answer in the form we keep demanding. This is where the black hole becomes more than an object. It becomes an interrogation chamber for reality. Every escaping quantum of Hawking radiation carries away a little energy, but also a deeper accusation. If you are only heat, where is the history? If you are only thermal, where is the difference? If you are the black hole's final voice, why do you sound almost the same no matter what the black hole swallowed? A silent black hole was unsettling. A leaking black hole is worse. Because silence could still conceal memory. A whisper can reveal that memory is missing. The crisis did not begin because someone invented a wild theory. It began because Stephen Hawking took the existing theories seriously enough to let them damage each other. That is the part worth holding on to. The black hole information problem was not born from a lack of discipline. It was not created by mystical language, or by a taste for paradox, or by treating black holes as cosmic symbols instead of physical objects. It emerged from an act of precision. General relativity described the horizon. Quantum field theory described fields near that horizon. Thermodynamics insisted that entropy and temperature were real physical quantities, not decorative metaphors. And when those pieces were placed together, the result was almost unbearable. A black hole could radiate. A black hole could lose mass. A black hole could eventually disappear. And the radiation, at least in the first calculation, seemed to carry no detailed memory of what had formed the black hole in the first place. This is the turning point where black holes stop being strange objects and become a threat to the structure of explanation itself. Until then, a black hole could still be imagined as an extreme destination. Matter falls in, light cannot return. The outside loses contact, disturbing but contained. The universe has built a region from which signals do not escape. But evaporation changes the status of the problem. It turns separation into possible erasure. To see the violence hidden inside that statement, begin with something simple. Imagine two stars with the same total mass, the same electric charge, and the same spin. One star was ordinary, mostly hydrogen and helium, burning through its nuclear life until collapse became inevitable. The other was artificial in the most impossible sense, assembled from a fantastically precise arrangement of particles, carrying a hidden message in its microscopic state. A physical difference woven into the exact correlations among its constituents. Let both collapse. From the outside, after the violence settles, the two black holes can look identical. The same mass, the same charge, the same spin. The exterior has lost almost everything that made the two histories different. Classical relativity can live with this, because it does not have to say the details have been destroyed. The details cross the horizon. They still belong to the full space-time, even if no outside observer can receive them. The black hole interior becomes the place where the difference survives. But Hawking radiation drains the black hole. Slowly, faintly, with a patience that makes the human lifespan irrelevant, the black hole gives energy back to the outside universe. If the process continues to the end, there is no permanent interior left to carry the hidden distinction. There is only the radiation field spread across space. Then the question sharpens. Can the final radiation tell the difference between those two beginnings? If it can, then black holes do not destroy information. The information must be encoded in the radiation, perhaps in correlations so delicate that they would never appear in Hawking's simplest thermal description. If it cannot, then the universe has committed a forbidden compression. Two distinct initial states have become one final state. The future has failed to preserve the difference between possible pasts. That is not merely a black hole problem. That is a wound in quantum mechanics. Quantum mechanics is often described as probabilistic, and that word can mislead. It makes the theory sound loose, as if it is comfortable with blur. But beneath the probabilities is an extremely rigid form of evolution. The quantum state may assign probabilities to future measurements, but the state itself evolves according to mathematical rules that preserve its structure. In the standard formulation, if you know the complete state now, the laws tell you how that state transforms. Different complete states do not simply collapse into the exact same complete state by ordinary time evolution. This property is called unitarity. The word is technical, almost dry, but its implication is severe. Unitarity is one of the reasons physics can keep a meaningful relationship between past and future. It says the total evolution does not erase distinctions at the fundamental level. The world can become impossible to reconstruct in practice, but not because the laws have thrown away the information. The distinction survives in the complete state, however scattered, hidden, or entangled. A burning book obeys this severe mercy. A black hole, if Hawking's original conclusion is taken literally, may not. That is why the radiation's thermal character matters so much. Thermal radiation is not empty of all information in an everyday sense. It can tell you temperature, it can tell you energy distribution, it can tell you broad statistical facts, but it does not obviously encode the precise microscopic identity of what made the black hole. A cloud of thermal photons does not seem to carry the detailed biography of a collapsed star. The black hole appears to speak only in averages. Physics cannot afford averages at the deepest level. Averages are what finite creatures use when the details are too numerous. Temperature is an average. Pressure is an average. Entropy is a counting of possibilities beneath what looks the same macroscopically. These concepts are powerful because they compress reality into manageable form. But compression is not supposed to be the last word. Beneath the average, there should still be a finer description. If the black hole's final radiation contains only the average, then the fine description has been lost. This is why the paradox was so shocking. It did not ask whether humans can recover what fell into a black hole. No one seriously expects a civilization to collect every quantum of Hawking radiation from an evaporating black hole and reconstruct a diary, a planet, or a star. Practical recovery is irrelevant. The question is whether the information exists in principle in the final state. Physics is often more interested in principle than possibility. A thing can be impossible for all real observers and still possible in principle. That distinction matters. You cannot unmix a cup of coffee after cream has spread through it. Not with your hands, not with any practical machine. But the microscopic laws do not say the information vanished. They say you have lost control of too many details. A black hole threatens to make, in principle, fail. That is a colder kind of impossibility. No laboratory incompetence, no lack of computing power, no practical limit caused by complexity. A fundamental many-to-one map from past to future. A universe in which the exact physical differences that once existed are no longer anywhere. The paradox was not born from ignorance. It was born from taking our best theories seriously. That is why it became impossible to dismiss. One could try to reject Hawking radiation, but the calculation came from quantum field theory, used with extraordinary care in curved space-time. One could try to say information loss is acceptable, but then quantum mechanics would have to be rewritten in a way that does not break everything else it explains so well. One could try to hide the information in a remnant, a tiny leftover object after evaporation. But such remnants introduce their own difficulties. One could try to let the information escape, but then the horizon cannot remain as innocent as classical relativity made it seem. Every exit damages something. And so the black hole becomes less like an object and more like a trial. It places the principles of physics on opposite sides of the same fact and refuses to let either side leave unchanged. General relativity says the horizon is real. Quantum mechanics says information must be preserved. Hawking radiation says the black hole can vanish. Thermodynamics says the black hole has entropy. The no-hair idea says the exterior is simple. Together, they form a question too precise to ignore. What, exactly, does the universe remember? Not what do we remember, not what can we measure, not what can be reconstructed by a future intelligence with impossible machines. What does reality itself retain? If the answer is everything, then black holes must be far stranger than the classical picture suggests. Their radiation must be more than heat. Their horizons must be less simple than they look. Their interiors may not be independent in the way we imagine. The information may be smeared across boundaries, hidden in entanglement, encoded in correlations, or protected by a layer of theory deeper than space-time. If the answer is not everything, then quantum mechanics has met an exception at the edge of gravity. Neither answer is comfortable. That was Hawking's gift and wound. He did not merely show that black holes have a temperature. He made them mortal, and by making them mortal, he took away the last easy hiding place for whatever they swallowed. A permanent black hole could be a prison. An evaporating black hole becomes a question of whether the prisoner ever existed. Information is a word too soft for what it means here. It sounds human. It sounds like books, messages, passwords, memories, the contents of a hard drive, the pattern of ink on a page. It sounds like something minds use after matter has already done the serious work, an extra layer placed on top of the physical world. That intuition is useful in ordinary life. It is almost fatal near a black hole. When physics speaks about information, it is not speaking primarily about meaning. A sentence and a random string of letters can carry different meanings to a reader, but the universe is not reading them as literature. The deeper question is whether the physical arrangement that made one state different from another remains distinguishable in the total evolution of the world. Information, in this sense, is the difference between possible realities. A coin heads up is not the same as a coin tails up. An electron in one spin state is not the same as an electron in another. A cloud of particles arranged one way is not the same as the same particles arranged differently. The distinction may become hidden, scrambled, entangled with an environment, or practically impossible to retrieve. But if quantum mechanics is right, the distinction is not simply erased by ordinary physical evolution. This is why the word carries such weight. It is not a diary of what happened. It is the fact that what happened was one thing and not another. The universe, at the deepest level, is not supposed to confuse them. This does not mean the universe is easy to read. Most information in real systems becomes inaccessible with terrifying speed. A dust grain collides with air molecules and becomes entangled with its surroundings. Light bouncing off your hand carries away microscopic traces. A warm room is a storm of correlations spreading outward faster than any observer can collect. The world is not secretive because it lacks records. It is secretive because it records too much in too many places. That is the strange mercy of quantum mechanics. It permits ignorance. It does not easily permit deletion. In classical life, we are surrounded by practical irreversibility. Eggs do not unbreak. Smoke does not reassemble into paper. A footprint on wet sand collapses under waves. Human memory fails. Archives burn. The arrow of time feels like a law of loss. At the scale of human action, that feeling is honest. We do not reverse the world. We endure its one-way drift. But the microscopic laws are more subtle. In many fundamental descriptions, a complete state evolves in a way that preserves the information needed, in principle, to relate past and future. The apparent irreversibility comes from coarse graining, ignoring fine details, averaging over microscopic states, and losing track of correlations dispersed into the environment. We simplify reality until it looks forgetful. The forgetting is ours. This is the hardest point to carry into the black hole problem, because the human mind keeps asking the wrong question. Can we recover the information? Recovery by us is not the issue. We are fragile, local, slow, and finite. The universe has never promised that its records would be accessible to primates with detectors. The real question is sharper. Does the information still exist in the complete physical state? If a black hole evaporates and the final radiation is all that remains, then the radiation must somehow contain the distinctions among all possible things that form the black hole, not as images, texts, or memories, but as physical correlations, as patterns in the quantum state, as subtle relationships between emitted quanta that preserve the difference between one collapsed history and another. If those distinctions are absent, then something radical has happened. Reality has mapped many different beginnings to the same ending. That is the point where the language of heat becomes dangerous. A thermal object does not care much about its detailed origin. A hot coal, a heated stone, and a metal plate can emit radiation described by temperature and spectrum. Thermal description is powerful because it washes over details. It replaces biography with statistics. For ordinary objects, this is not a fundamental loss. The details are still somewhere, tangled in the object and its environment. But if a black hole evaporates completely into radiation that is exactly thermal, with no hidden correlations carrying the missing distinctions, then statistics have become the final reality. The biography has not been hidden, it has been abolished. Quantum mechanics recoils from that. Not emotionally, structurally. A quantum state can be uncertain without being careless. It can contain probabilities without giving up precision. Before measurement, a state may not assign definite classical properties in the way intuition wants, but that does not make the theory vague. The quantum state encodes amplitudes, phases, and correlations with discipline. Its evolution is not a casual drift from one blur to another. It is constrained. This is why information is preserved does not mean everything stays recognizable. It means the complete state does not lose the distinctions that make one possible history different from another. You may never decode them, you may never know where to look, but in principle, the final state must be rich enough to contain what the initial state demanded. The black hole asks whether that richness survives gravity's deepest trap. At the quantum level, what falls in is not merely stuff, it is state, it is correlation, it is entanglement with the outside world. A particle entering a black hole may be part of a larger quantum relationship extending beyond the horizon. If the black hole later evaporates, that relationship must be accounted for. The problem is not just inside versus outside. It is whether the entire web of quantum distinction remains consistent. This is why the paradox becomes so severe when entanglement enters the story. Hawking radiation is produced in a way that entangles degrees of freedom across the horizon in the simplex picture. Early radiation leaves, later radiation leaves. The black hole shrinks. If the radiation is to purify itself, if the final state is to preserve information, then later radiation must be correlated with earlier radiation in a specific way. But the same later radiation also seems tied to interior partners near the horizon. The bookkeeping becomes almost impossible under the old assumptions. Something must be reinterpreted. Perhaps the radiation was never perfectly thermal. Perhaps the horizon is not a simple causal boundary in the quantum theory. Perhaps the interior is encoded in the exterior in a way that ordinary geometry hides. Perhaps locality, as we understand it, is approximate. Perhaps space-time itself is not the arena where the deepest accounting happens. The word information has now forced the black hole to stop being a place. It has become a test of distinguishability. Information is not what a mind knows. It is what reality must still be able to distinguish. And this is why the missing thing cannot be found, like a particle in a detector or a substance behind the horizon. It is not an object, it is a requirement, a demand placed on every possible future by every possible past. If the demand survives, then black holes are not destroyers. They are the most extreme scramblers in nature, hiding the record in forms too subtle for ordinary space-time to explain. If the demand fails, then the laws beneath quantum theory are less absolute than we believed. Either way, the black hole has already changed shape. It is no longer merely dark. It is no longer merely dense. It is no longer merely a boundary where light cannot escape. It is a question written in gravity. Can reality still tell the difference? A universe that forgets is not merely mysterious. It is less lawful. That sentence sounds too severe until the black hole forces it into view. We are used to thinking of lawfulness as regular behavior. Planets orbit, light bends, atoms emit spectra, falling bodies accelerate. If a prediction works, we call the world lawful. But beneath prediction sits something more fragile, the assumption that reality has a consistent relation to itself across time. The future does not have to be easy to calculate, but it must not be disconnected from the past. Information is the thread. Cut the thread, and physics does not simply lose a detail, it loses the reason details matter. This is why the black hole information problem is not a specialized puzzle locked inside astrophysics. It is not only about collapsed stars or event horizons, or what happens to objects after they cross a boundary no telescope can penetrate. It reaches into the structure of explanation. It asks whether the laws of nature merely describe what appears, or whether they preserve a deeper accounting of what has existed. Imagine a universe where information can be genuinely destroyed. Not hidden, not scrambled, not mixed into heat, destroyed. In such a universe, the same final state could arise from different initial states, with no remaining distinction anywhere. The past would not merely be unknowable to observers, it would be physically underdetermined by the present. Reality would contain outcomes that had thrown away their ancestry. At first, that may sound tolerable. Human life already feels that way. We do not know which raindrop struck a river first. We cannot reconstruct every gust of wind from the shape of a cloud. History is filled with vanished causes and unrecoverable details. But these are limits of access. The world has spread the evidence too thin for us. The difference still matters microscopically, even if no one can gather it. A fundamental loss of information would be colder. It would mean the evidence is not thin. It is absent. Quantum theory is not built for that absence. Its ordinary evolution is strict in a way that everyday randomness conceals. When a quantum system evolves without measurement-like interaction with an uncontrolled environment, its state changes according to rules that preserve total information. The mathematics may produce probabilities for what an observer sees, but the evolution of the full state is not a careless many-to-one collapse. It keeps track of possibilities with a precision that feels almost inhuman. This is why the information paradox became a crisis of trust. If black holes can erase information, then quantum mechanics is incomplete in a way deeper than adding a missing particle or correcting a parameter. The theory's ordinary grammar would require revision, not just near black holes perhaps, but anywhere gravity and quantum evolution touch the same event. A small exception at the horizon might not stay small. Fundamental principles are not decorative. They hold structures together. To change one is to create pressure everywhere. And yet general relativity has its own dignity. It is not a weak theory waiting to be dismissed by quantum mechanics. It took gravity out of the language of force and rebuilt it as geometry. Matter and energy tell space-time how to curve. Curved space-time tells matter how to move. The theory has passed test after test, from Mercury's orbit to gravitational waves crossing the cosmos. When it predicts horizons, it does so from a structure that has earned its authority. So the problem is not that one theory is obviously foolish. The problem is that both are serious. General relativity says an event horizon can form, a causal boundary beyond which signals do not return. Quantum mechanics says the complete evolution of physical states should not erase distinctions. Hawking radiation says black holes are not eternal vaults. Thermodynamics says black holes have entropy and temperature. None of these statements is cheap. None can be thrown away without consequence. The black hole becomes the place where trusted truths stop fitting in the same room. That is the deeper implication. The object in the sky is not only an object in the sky. It is a negotiation between principles. It asks what must be preserved when preservation seems impossible. It asks which part of reality is most fundamental: locality, unitarity, smooth space-time, the equivalence principle, or the idea that the interior of a region is independent from its boundary.
Each answer cuts.
If information is truly lost, quantum mechanics must bend. If information escapes, the horizon cannot be as simple as classical relativity suggests. If the information is stored on the surface, then volume is less fundamental than it looks. If the interior is encoded outside, then space is not the container we imagined. If violent new physics appears at the horizon, then falling freely through a large black hole may not be the calm passage general relativity promised. The paradox does not produce discomfort because it is vague. It produces discomfort because it is overconstrained. Too many good principles demand to survive. This is why black holes are so different from ordinary mysteries. A mystery often invites us to search for missing facts. Here, facts are not enough. We have equations, we have tested frameworks, we have thermodynamic arguments, we have quantum rules, we have astronomical evidence that black holes exist as real astrophysical objects. The missing piece is not merely empirical, it is conceptual, a way to let the principles coexist without quietly betraying one another. In that sense, black holes are not holes in space. They are holes in our hierarchy of explanation. They show us that the universe may be lawful at a level we have not yet reached, while appearing contradictory at the level where our best theories meet. That is not comforting. It does not mean anything goes. It means the opposite. The contradiction is sharp because reality is constrained. The escape route, if it exists, must be precise enough to preserve what needs preserving without inventing drama where the science does not permit it. A real solution must not merely sound profound. It must do the bookkeeping. That bookkeeping is where the word information becomes almost moral in the structure of physics. Not moral as humans use the word, not good or evil, not purpose, not intention. Moral in the older sense of obligation. The laws seem obligated to distinguish what is physically distinct. They can hide the difference. They can scatter it through a million degrees of freedom. They can make it irrecoverable to any practical observer. But if they truly delete it, they change their own character. The universe would become less reversible, less exact, less accountable. This is the pressure black holes place on the foundations. They say, if your laws are real, show where the record goes. Do not say inside if the inside disappears. Do not say thermal radiation if the radiation carries no distinction. Do not say lost to observation if you mean lost from existence. Do not hide an ontological wound behind the language of practical ignorance. The black hole does not allow sloppy grief. It forces precision. And precision is what makes it frightening. The popular imagination makes black holes monstrous because they are dark and massive, but their true severity lies in their cleanliness. The horizon is clean, the exterior description is clean, the thermodynamics is clean, the radiation calculation is clean. The paradox is clean. A clean contradiction is harder to escape than a messy one. Mess can be blamed on missing details. A clean contradiction exposes the architecture. That is why the story no longer belongs only to astronomy. It belongs to the question of what kind of universe this is. A universe of objects moving through space? A universe of fields evolving through time? A universe of quantum states preserving distinctions? A universe where geometry emerges from something deeper. The black hole does not answer directly. It applies pressure until the question changes. At first, we ask what happens to matter when it falls in. Then we ask what happens to information. Then we ask what information is. Then the question widens until it touches everything. What must reality preserve in order to remain reality? A universe that forgets is not merely mysterious. It is less lawful. And if black holes do not let it forget, then they are not cosmic erasers. They are something stranger and more severe. The places where reality hides its memory so deeply that space and time themselves may have to be rebuilt to explain where it went. The question changes shape when the black hole is given entropy. Entropy is the clue that refuses to behave. For ordinary matter, entropy grows with volume. A box of gas has more possible microscopic arrangements when the box is larger. Give the molecules more room, and the number of hidden configurations rises. The logic feels natural because we imagine information living inside things, in the volume of the box, in the bulk of the star, in the interior of a room, in the three-dimensional space where the physical stuff resides. Black holes broke that intuition. Their entropy does not scale like volume. It scales like area. More precisely, the entropy of a black hole is proportional to the area of its event horizon, not the volume hidden within, not the amount of interior space one might naively imagine behind the boundary. The surface area of the horizon, the two-dimensional measure wrapped around the darkness. That fact is so quiet it can pass by too quickly. It should not. Because entropy is not merely heat's shadow. It is a measure of how many microscopic states can correspond to the same visible description. It is a way of counting hidden possibility. If a black hole has entropy, then a black hole has microscopic degrees of freedom, or at least behaves as if it does. There must be some underlying accounting that explains why a black hole with a certain horizon area can represent so many possible internal states. But the number is written on the boundary, not in the volume. This is where the black hole stops being only a problem about loss and becomes a problem about location. Where is the information? If a black hole contains the records of everything that formed it, why does the bookkeeping seem to care about the horizon's area rather than the hidden interior's volume? Why does the surface know how much can be stored? The old intuition says the world is three-dimensional. A region of space contains things. A boundary surrounds them. The inside is primary, the surface is secondary. The surface tells you where the thing ends. It does not carry the full reality of what the thing is. Black holes suggest a colder possibility. Perhaps, in gravity, the boundary is not merely a wrapper. Perhaps it is the ledger. This is the midpoint where the original question becomes too small. We began with a dramatic claim about CERN and something missing from black holes. We corrected it. We called the missing thing information. We followed that information into the horizon, into Hawking radiation, into the fear that a black hole might evaporate without returning the distinctions it consumed. But now, the deeper question is no longer simply whether information survives. It is where reality stores it. That shift is enormous. It moves the subject from a question about black holes to a question about space-time itself. If the information inside a region can be represented by data associated with its boundary, then space may not be the kind of container the mind assumes. The interior may not be independent in the way ordinary objects train us to believe. The abyss may not be deep. It may be written flat. This idea became known, broadly, as holography. The word is dangerous because it invites cheap imagery. The universe as a projection, reality as illusion, life as a simulation. Those phrases are too loose. They turn a precise physical clue into decorative unreality. The serious version is sharper and more disciplined. Holography suggests that, in a theory of quantum gravity, the information content of a region may be encoded on a lower dimensional boundary, much as a hologram can encode a three-dimensional image on a two-dimensional surface. Not because the world is fake, because gravity seems to count differently. Black holes are the evidence that force the thought. If the maximum entropy in a region is set by area rather than volume, then nature may be placing a limit on how much information a region can contain, and that limit is written in terms of surfaces. Pack too much energy into a region, and it collapses into a black hole. The black hole's entropy is then set by its horizon area. The boundary becomes the maximum account. That is not how ordinary intuition expects information to behave. A library stores books in its rooms, not only on its walls. A body stores structure in organs, cells, blood, bone, and nervous tissue, not merely on skin. A planet contains layers beneath its surface. Depth matters, volume matters, interior matters. But gravity has a way of making familiar words unstable. Inside a black hole, the meaning of inside is already infected by causal structure. Time and space do not keep their ordinary roles. The horizon is not a shell one can peel away. The interior is not simply a room behind a door. If the black hole's entropy is measured by area, perhaps that is not an odd detail. Perhaps it is a sign that the geometry we experience as interior volume is not the fundamental storage space of the theory. Perhaps the record of the interior is somehow present at the boundary. This possibility does not solve everything by itself. It opens a deeper route. The holographic principle became one of the most powerful ideas in the search for quantum gravity, because it suggests a way for information to be preserved without requiring it to escape the horizon in the naive sense. The information might never have been localized inside in the simple way we imagined, or the distinction between inside and outside might be less fundamental than the classical picture requires. The black hole would then not be violating the universe's memory. It would be revealing that we misunderstood where memory lives. The strongest mathematical realization of this idea appears in theoretical settings such as the ADS/CFT correspondence, where a gravitational theory in a higher dimensional space can be equivalent to a quantum theory without gravity on its boundary. That is not a direct description of our universe in its ordinary cosmological form, and it should not be treated as a completed answer to every black hole in nature. But its existence changed the emotional temperature of the problem. It showed that holographic encoding was not merely a metaphor. In some carefully defined worlds, it could be mathematics. And once mathematics shows that an interior gravitational reality can be equivalent to boundary information, the old picture of space loses its innocence. A black hole is no longer only an object that swallows things. It becomes a warning that the deepest description of a region may not reside where the region appears to be. This is hard to accept because perception is volume-based. We move through rooms, we reach into boxes, we place objects behind other objects. We associate reality with occupancy. A thing is real because it takes up space. A memory is stored because something inside a device has changed. A body exists because its interior is filled with structure. The mind is trained by containers. Black holes make containers untrustworthy. They show that the most information-dense objects in the universe do not advertise their capacity through depth. They count through area. Their horizons behave less like surfaces of objects and more like pages on which gravitational reality has written its maximum number of hidden states. This is the second ignition. The real question was never only, what happens to what falls into a black hole? It was also, what is a place? If the information of a region can be encoded on its boundary, then place is not merely where things are. Place may be an emergent way of describing relationships in a deeper quantum structure. The interior may be reconstructed from entanglement. Geometry may arise from patterns of information. Distance may be less fundamental than correlation. Now the black hole is no longer at the edge of space. It is at the edge of the idea of space. And this is why the missing information cannot be imagined as a lost object floating somewhere in the dark. It may be encoded in a way that our ordinary geometry does not know how to picture. It may be preserved not by traveling out through the horizon, like a message in a bottle, but by never belonging exclusively to the interior in the first place. The abyss changes shape. It stops being a bottomless depth. It becomes a surface too precise for the eye to read. Space begins to look less solid once information takes the weight. That is not how the world feels. Space feels like the most obvious thing there is. It is the room before the furniture, the distance before the journey, the emptiness in which objects appear, move, collide, separate, and disappear. Matter may change, light may bend, time may slow, but space, to ordinary intuition, remains the stage. Black holes make the stage suspicious. If the entropy of a black hole scales with area, if the information content of a region can be tied to a boundary, if theory can construct worlds where gravity in a volume is equivalent to a quantum description on a lower dimensional edge, then space can no longer be treated as the unquestioned container of reality. It may be assembled, emergent, something that appears only after deeper relationships organize into the geometry we mistake for a starting point. The word emergent can sound harmless. It is not. A wave is emergent. No single water molecule is the wave. Temperature is emergent. No single molecule has the temperature of a room. Temperature is a statistical description of many microscopic degrees of freedom. Solidity itself is emergent in a sense. The hard surface of a table is not hard because matter is full in the way the hand imagines. It is hard because electromagnetic forces and quantum rules resist compression. The familiar world is already built from things that are not what they seem. But space feels different because it feels prior. Even when we learn that matter is mostly empty, even when relativity teaches that space and time are woven into space-time, the mind still quietly places all phenomena somewhere. It needs a where before it can imagine a what. Black holes threaten that order. They suggest that the where may itself be produced by the what, or, more precisely, by patterns of quantum information and entanglement that do not live inside space in the ordinary way, because they are part of what allows space to be described at all. The black hole information problem does not stay confined to the horizon. It spreads outward into the meaning of distance, locality, interior, boundary, and object. If information is preserved, but not preserved in any simple interior location, then the universe may be protecting its memory through a structure deeper than the geometry we see. The event horizon becomes less like a prison wall and more like a clue that the map itself has been drawn from hidden rules. Entanglement is one of those rules. In quantum mechanics, systems can share a relationship stronger than ordinary correlation. Measure one part, and the description of the other is constrained, even across distance. This does not allow faster-than-light messaging, but it does show that the complete state of reality is not always built from independently existing pieces with separate private descriptions. The whole can be more fundamental than the parts. Black holes push this fact to an extreme. Hawking radiation is entangled. The interior and exterior descriptions become woven together in ways classical geometry does not easily accommodate. If the information comes out, it likely comes out not as a readable inscription stamped onto individual particles, but as correlations distributed across the radiation. The message, if it exists, is not in one photon. It is in the relationships among many. It is structure spread across the state. That thought reaches beyond black holes. Perhaps geometry itself is built from relationships. Perhaps distance is not fundamental separation, but a measure arising from patterns of entanglement. Perhaps regions are near each other because the underlying quantum degrees of freedom are strongly connected, and far apart because they are weakly connected. Perhaps the smoothness of space-time is the large-scale appearance of an informational network too fine for direct perception. These are not settled facts about our universe. They are active ideas at the edge of theory, supported in some mathematical settings and still developing in others. The caution matters. It is easy to turn holography and emergent spacetime into slogans. The science is more disciplined than slogans allow. It does not say, cheaply, that nothing is real. It says reality may be real in a way our categories were not built to hold. Space may be what information feels like when it is organized enough to look continuous. That line is not an explanation by itself. It is a direction of pressure. The pressure comes from black holes because they combine gravity, entropy, quantum fields, and causality into one object. A black hole is not simply dense. It is information dense in a way that saturates a gravitational limit. Add energy to a region beyond a certain point, and the region does not become a denser library in the ordinary sense. It becomes a horizon. The maximum information does not keep increasing with volume. It is measured by area. Gravity enforces a different accounting. This is why the black hole is not an exception at the edge of physics. It may be a rule revealed in extreme form. Ordinary space hides the rule because ordinary regions are weakly gravitating. A room does not collapse when filled with books. A planet does not announce the holographic limit in daily experience. Our scale is forgiving. It allows the illusion that volume is the natural home of information, that objects simply sit inside containers, that boundaries are secondary. The black hole removes the forgiveness. It compresses energy until geometry responds with a horizon. It turns hidden microstates into entropy proportional to area. It forces quantum theory to ask how information is returned. It forces relativity to confront the possibility that the interior is not independent in the way the classical picture suggests. It forces thermodynamics to speak in the language of surfaces. The result is a reversal almost too large to feel at first. We thought black holes were places where space becomes extreme. They may be places where space reveals that it was never fundamental enough. This does not mean space is an illusion in the casual sense. Space does not vanish. It works. It measures. It bends starlight. It carries gravitational waves. It expands between galaxies. It tells matter how to move. The point is not that space is fake. The point is that space may be like temperature, real, measurable, indispensable, and still not the deepest layer. Temperature is real, but beneath it are molecules. Space-time is real, but beneath it, perhaps, are quantum relations whose organized behavior becomes geometry. If that is true, then the black hole information problem is not asking for a small repair. It is asking us to change the order of explanation. We do not begin with space, place matter inside it, and then ask where the information went. We may have to begin with information, correlations, and quantum structure, then ask how something like space emerges well enough to contain stars, bodies, laboratories, and horizons. The black hole turns the question inside out. Instead of asking how information moves through space, we begin to ask how space may arise from information. That is a different abyss. Not a hole in the sky, but a hole beneath the concept of location. A place where the deepest laws seem to whisper that what we call distance may be secondary, that what we call interior may be reconstructed, that what we call a boundary may carry more of reality than the volume it surrounds. The horizon no longer looks like an ending. It begins to look like a translation surface. On one side, gravity speaks as geometry. On the other, quantum theory speaks as information. The black hole stands between them, refusing to let either language remain alone. And somewhere in that refusal is the expanded meaning of the missing thing. Information was not merely missing from black holes. It may be what space-time was made to protect. The human mind was not built for horizons. It was built for ground, walls, weather, hunger, faces, tools, fire, distance that can be walked, danger that can be seen, objects that remain objects when no one is looking at them. It learned the world by touching surfaces. It learned cause and effect from impacts, wounds, falling stones, broken branches, shadows moving with the sun. Its deepest instincts were trained inside a narrow band of reality, where space behaves gently, time feels universal, and information loss usually means no one can find the record anymore. Then it tries to think about a black hole. The failure is almost guaranteed. Not because the mind is weak, because the mind is local. It expects the world to be assembled from nearby pieces. This object here affects that object there by sending something across the distance between them. A signal travels, a force is felt, a cause precedes an effect. A surface encloses an interior. A boundary separates what is inside from what is outside. These habits are not foolish. They work beautifully in the scale where bodies live. They are the reason hands can build machines and eyes can navigate rooms. But a black hole takes those habits into a place where they stop being reliable. At the horizon, the ordinary idea of a boundary becomes underqualified. A boundary in everyday life can be crossed in either direction if the body has the right path. A wall blocks motion because matter resists matter. A membrane can be pierced. A border can be crossed. But an event horizon is not made of material resistance. It is made of causal structure. Once crossed inward, the future no longer contains outward escape. That already offends intuition. Yet the deeper offense comes when quantum theory enters, because quantum theory does not allow the world to be built only from local common sense. A quantum state can describe correlations that cannot be reduced to little private facts carried by each part. Entanglement means the whole has a structure not exhausted by its separate pieces. The parts may be far apart, but the complete description still binds them. The mind wants a story made of objects. Physics gives it a state. This is why every simple answer to the black hole information problem begins to damage something. Suppose the information stays inside. That feels natural. Things fall in, the record goes with them, the horizon keeps it hidden. But if the black hole evaporates completely, where does the interior record go? A hiding place that disappears cannot remain a hiding place forever. Suppose the information comes out in Hawking radiation. That saves quantum mechanics. But the classical horizon was supposed to prevent any signal from the interior from returning to the outside. If the radiation carries detailed information, then either the information was never simply trapped inside, or the horizon is not behaving like the clean causal boundary general relativity promised. Suppose the information is stored on the horizon. That fits the area law and holographic hints. But then the interior is not independent in the ordinary way. The surface is not merely surrounding the volume, it is somehow accounting for it. The common sense picture of a thing occupying space begins to fail. Suppose the information is destroyed. That preserves the simplicity of the horizon and the thermal character of the radiation. But now, quantum mechanics is wounded at the foundation. The future no longer preserves the full distinctions of the past. Every option demands tribute. This is what makes the paradox so hard to reduce to a clean visual image. It is not one object doing one strange thing. It is a set of principles refusing to fit together inside the same intuitive frame. Locality says events influence each other through nearby interactions and signals limited by light. The equivalence principle says that, for a large enough black hole, an observer crossing the horizon should not encounter anything locally dramatic at that moment. Unitarity says quantum information should be preserved. Semi-classical physics says Hawking radiation emerges from quantum fields around the horizon. Entanglement says the radiation and interior cannot be treated as independent in the simple way the old picture wants. Keep all of them, and the structure strains. Give up one, and the cost spreads. The firewall debate made that cost vivid. If information must come out in the radiation, and if late radiation must be correlated with early radiation to preserve unitarity, then the same late radiation cannot also be entangled in the usual smooth way with interior partner modes behind the horizon. Quantum entanglement has limits. It cannot be freely shared with everything at once. This tension led some physicists to propose that the horizon might not be smooth after all, but replaced by something violent. A firewall that would burn infalling observers at the boundary. That possibility is not established fact. It is a warning. It says that saving the information may require sacrificing the calmness of the horizon. But sacrificing that calmness means wounding one of general relativity's most elegant promises, that free fall through the horizon of a large black hole should feel locally ordinary, at least until tidal forces become severe deeper in. The mind wants one betrayal. The paradox offers several. This is where common sense becomes not wrong, exactly, but too small. It expects the solution to resemble a mechanism. Information leaks through a crack, or hides in a core, or escapes through a tunnel, or remains in a remnant. But each image imports ordinary space, ordinary time, ordinary containers, ordinary motion. The black hole problem may require a description in which those images are not fundamental enough to survive. At the horizon, common sense does not die dramatically. It becomes underqualified. That is more disturbing than being wrong. A wrong intuition can be replaced by a better picture. An underqualified intuition cannot even hold the right kind of picture. It keeps asking where the information is, as if where were the primitive fact. It asks when the information escapes, as if time near the horizon were simple. It asks what is inside, as if inside and outside were independent containers waiting to be inventoried. The deeper theory may not answer in that grammar. It may say that the information is preserved in correlations, spread across radiation. It may say that the interior is encoded non-locally in exterior degrees of freedom. It may say that space-time geometry emerges from entanglement, so the question of location must be reconstructed rather than assumed. It may say that smooth horizons are approximate features of a semi-classical description, valid only until quantum information accounting becomes unavoidable. None of these answers is emotionally easy, because none lets the world return to the scale at which intuition was born. This is the price of approaching black holes, honestly. The viewer wants a monster, and science gives a limit of cognition. The eye wants darkness. The equations reveal a boundary where words like inside, outside, surface, storage, escape, and loss begin to lose their childhood meanings. The black hole does not merely defeat escape velocity. It defeats inherited categories. And once those categories fail, the problem becomes sharper rather than softer. The universe is not becoming mystical. It is becoming less human. It is refusing to preserve the furniture of our imagination just because that furniture once helped us survive. A horizon is not a wall. Radiation is not necessarily a confession. Entropy is not just disorder. Information is not knowledge. Space may not be the container. And the black hole is not asking us to imagine something bigger, darker, or more powerful. It is asking us to think without the tools that made thinking feel natural. Every proposed escape route looks, at first, like mercy. Let the information come out. Let the horizon keep its smoothness. Let quantum mechanics remain intact. Let relativity survive where it has already proved its elegance. Let the black hole evaporate without turning the universe into a machine that forgets. Somewhere, surely, there must be a quiet adjustment, a hidden term in an equation, a subtle correction that allows every principle to keep its dignity. But black holes rarely offer mercy without a price. The information paradox does not behave like a locked door waiting for the right key. It behaves like a chamber where every key changes the shape of the lock. Solve one problem, and the solution reaches backward into assumptions that once felt untouchable. Preserve one law, and another begins to tremble. This is why the history of the paradox is filled not with clean endings, but with trade-offs. One possibility is simple and brutal. Information is truly lost. Hawking himself once took this seriously. Perhaps black holes are the rare places where quantum evolution is not unitary. Perhaps gravity permits the universe to turn pure states into mixed states, detailed beginnings into statistical endings. The black hole evaporates, the radiation remains, and the fine distinctions of the past are gone. That answer has the advantage of following the original. It also cuts into quantum mechanics at the root. If information loss is allowed, it cannot be treated as a tiny local embarrassment. Quantum theory's structure depends on a disciplined relation between past and future. Break that relation near black holes, and the break must be contained with extraordinary care. Otherwise, the wound may spread into energy conservation, causality, prediction, and the consistency of physical law. A universe that forgets only at horizons must explain why the forgetting does not leak into everything else. Another possibility is that the black hole does not fully evaporate. Perhaps it leaves behind a remnant, a tiny final object, possibly near the Planck scale, carrying all the information that ever fell in. The archive survives because the vault never completely disappears. At first, this feels almost elegant. The problem was that the hidden record had nowhere to go. A remnant gives it somewhere. The black hole shrinks until it reaches a final core, a last seed of memory too small for our current theories to describe. But the remnant has its own burden. If an arbitrarily large amount of information can be stored in an arbitrarily tiny object, then that object must contain an enormous number of internal states. Physics must explain how such a thing exists, why it does not produce strange instabilities, and why tiny remnants would not appear in catastrophic abundance in ordinary processes. The remnant saves the archive by compressing the library into something smaller than a letter. A rescue can become another paradox. There is the possibility of baby universes. Perhaps information does not return to our exterior universe, but escapes into a disconnected region of space-time, a new branch pinched off behind the horizon. What looks like loss from our side may be transfer into another domain. This has a poetic severity. The record is not destroyed, it leaves. But for observers in our universe, the result may still resemble information loss, unless the full theory includes the other branch in its accounting. And the idea demands a quantum theory of space-time topology far beyond the settled ground. It shifts the question from evaporation to cosmic bookkeeping across regions that may not remain part of our observable world. Then there is complementarity, a more subtle response. Perhaps no single observer can witness a contradiction. To the outside observer, information is somehow processed and returned by the horizon. To the infalling observer, nothing special happens at the horizon, and the information passes inward. No one can compare both descriptions directly, because the horizon prevents the necessary communication. The two stories may be complementary rather than contradictory. This approach respects a hard lesson of relativity and quantum mechanics. What can be said physically may depend on what can be observed consistently. But complementarity walks a narrow ridge. If the same information seems to be both reflected at the horizon and carried inside, one must avoid illegal cloning of quantum states. Quantum information cannot simply be copied. The outside and inside descriptions must not become two independent versions of the same state. The escape works only if the theory is careful enough to prevent any observer from using the apparent duplication to create a real contradiction. Again, the solution does not remove the pressure. It relocates it. Then came the firewalls. The firewall proposal was not born from a desire for drama. It emerged from trying to make the information accounting honest. If Hawking radiation is to carry information out, late radiation must be entangled with earlier radiation in the right way. But the smoothness of the horizon also seems to require entanglement between outgoing modes and partners behind the horizon. Quantum entanglement cannot be freely maximized with two independent systems at once. Something must give. One way to give is to break the smooth horizon. Instead of a calm crossing for the infalling observer, there may be high-energy violence at the horizon itself, a firewall. The boundary that general relativity made locally uneventful becomes physically lethal. The information is saved, perhaps, but the equivalence principle is wounded. This is why the firewall debate was so unsettling. It did not merely propose a dramatic object. It exposed a conflict among principles many physicists wanted to keep: unitarity, ordinary quantum field behavior near the horizon, and the smooth experience of freefall. The debate made visible the price of insisting that information comes out without changing anything else. The paradox does not ask for an answer. It asks what physics is willing to surrender. Holography offers another route, and perhaps the most powerful. If the information of a gravitational region can be encoded on a boundary, then the black hole interior may not be independent in the naive way. The horizon's area law becomes a clue, not an oddity. The radiation may carry information because the deeper theory never stored it in a simple hidden volume to begin with. This path has real mathematical strength in certain theoretical settings. It allows black hole evaporation to be compatible with unitarity in models where gravitational physics has an equivalent non-gravitational quantum description. It teaches that space-time locality may be approximate, not fundamental. It gives the paradox a language deep enough to speak both gravity and quantum information. But it also demands a sacrifice. The sacrifice is our ordinary picture of place. If holography is right in the relevant way, the interior of a black hole is not simply a room behind a locked door. It may be encoded in degrees of freedom associated with the boundary or the radiation, in a manner no classical map can display. The price of saving information may be admitting that space-time is not the deepest storage medium of reality. That is not a small correction. It is a change in ontology. Each proposed solution preserves something precious by making something else less innocent. Information loss keeps the horizon simple, but wounds quantum mechanics. Remnants preserve the record, but demand impossible compression. Baby universes save information globally, but remove it from our visible accounting. Complementarity avoids observer-level contradiction, but strains ordinary notions of inside and outside. Firewalls preserve unitarity by burning the smooth horizon. Holography protects information by demoting space-time from fundamental stage to emergent description. There is no free exit. The black hole sits in the center of theory like a debt that cannot be cancelled, only refinanced into deeper structure. Every time physics tries to pay it, the cost appears somewhere else, in locality, geometry, causality, equivalence, or the meaning of a region of space. This is the price of understanding, not confusion. Payment. The universe may preserve its memory, but not in the comforting language we first used to ask the question. To keep information, reality may have to be less like a collection of objects in a container, and more like a network of constraints, whose geometry is only the visible surface of a deeper order. The black hole does not merely hide the answer. It charges admission. And the admission price is the world we thought we were standing in. The first hint that the black hole may return what it swallowed is almost insulting in its subtlety. It does not look like a message. It does not look like an image of the star that collapsed, or a readable code printed on escaping particles, or a final confession from the horizon. It looks like radiation, almost featureless, almost thermal, a dim, patient leakage from an object that should have been silent. If the information comes back, it comes back disguised as the last place human intuition would search for memory. Correlation. That word is easy to underestimate. It sounds statistical, mild, a relationship between things after the real substance has been named. But in quantum theory, correlations can carry the architecture of a state. A single particle may tell you almost nothing. Two particles together may tell you more. A vast collection, examined not as isolated fragments but as a whole, may contain distinctions invisible to any local glance. The message may not be in the letters. It may be in the spacing between them. This is the shift required to understand why Hawking radiation might not be the final erasure it first appeared to be. The early calculation gave radiation that looked thermal. Thermal radiation is poor in biography. It tells you temperature, not history. But perhaps that was only the coarse description, the visible surface of a more exact quantum state. Perhaps the radiation is not perfectly featureless when examined with impossible precision. Perhaps the information is not carried by individual quanta, but by fine-grained correlations distributed across everything the black hole emits. A black hole, in this view, does not return a diary. It returns ash whose every mote is secretly arranged. The difficulty is that the arrangement is not practically usable. To reconstruct what formed an evaporated black hole, an observer would have to collect nearly all of the Hawking radiation across unimaginable timescales, preserve its quantum coherence, and measure correlations of unbearable complexity without destroying the very structure being studied. For an astrophysical black hole, this is not a difficult laboratory project. It is a fantasy of control beyond any civilization we can responsibly imagine. But again, physics is not asking whether we can read the record. It is asking whether the record exists. This distinction becomes visible through the idea known as the page curve. Imagine following the entropy of Hawking radiation over the lifetime of an evaporating black hole. If the radiation were exactly thermal and uncorrelated with the information inside, the entropy of the radiation would keep increasing as more radiation escaped. More radiation would mean more apparent ignorance. The final state would remain mixed, incomplete, unable to encode a precise initial state. But if evaporation is unitary, the pattern must be different. At first, the radiation can look thermal. Entropy rises. The black hole and its emitted radiation are entangled. The outside collection seems increasingly random. But after a certain point, often called the page time, the radiation must begin to purify. Later emissions must be correlated with earlier emissions, so that the total radiation state, once evaporation is complete, contains the full information. The entropy of the radiation rises, reaches a peak, and then falls. That downward turn is not just a curve. It is the universe refusing to forget. For decades, this remained more than a technical question and less than a settled answer. It was a demand placed on any complete theory of quantum gravity. Reproduce the page curve without cheating. Show how a black hole can radiate in a way that looks thermal at first, yet ultimately preserves information. Show how the fine-grained entropy behaves like unitary physics requires. Show where the semi-classical picture has been too naive. Recent theoretical developments involving quantum extremal surfaces and so-called islands have given physicists a more precise way to see this possibility in certain models. These ideas are technical, but their emotional meaning is severe. When calculating the fine-grained entropy of Hawking radiation in a gravitational setting, the correct accounting may include regions that seem, in the older geometric picture, to lie inside the black hole. These regions, called islands, can become part of the entanglement wedge of the radiation. In other words, the radiation's true quantum description may already include part of what naive spacetime called the interior. That sentence should feel unstable. The radiation outside may encode an island inside. Not because a signal escaped in the ordinary way, not because a particle smuggled a note across the horizon, because the deeper quantum gravitational accounting does not divide the world along the same lines that classical geometry draws. The boundary between inside and outside may be the wrong boundary for the information. This is where the mechanisms begin to converge. Hawking radiation made the black hole mortal. Entropy made the horizon informational. Holography made the boundary suspect. Entanglement made separateness incomplete. The page curve demands that the radiation eventually carry the record. Islands suggest that the record may be included in the radiation's description through a reconstruction of space-time itself. None of this means the paradox is casually solved in the sky. These are theoretical advances, often developed in simplified models and special gravitational settings. They do not mean a telescope has watched information emerge from an astrophysical black hole. They do not mean CERN has found the missing thing in a detector. They do not mean every conceptual cost has vanished. The caution matters because the real power of the story lies not in pretending the answer is finished, but in seeing how strange the honest answer may have to be. Information may come out, but it may come out in a form that destroys the old meaning of out. The black hole's final radiation may be pure, not because the horizon was secretly porous like a leaky container, but because the container was never the fundamental object. The outside radiation may encode the interior because quantum gravity assigns reality differently than classical space-time does. What looked like loss may have been an error in the way we divided the system. The message may not be absent. It may be written in a language no observer can practically decode. This is a profound reversal. The thermal glow that once seemed like evidence of forgetting becomes, under finer accounting, a possible disguise for memory. The radiation that looked too generic may contain structure hidden beyond local measurement. The black hole that seemed to erase may instead scramble more completely than anything else in nature, spreading the record across a final state so complex that only the laws themselves can be said to read it. There is no comfort in this. A preserved record is not a recovered world. The star does not return. The book does not reform. The falling body does not climb back out. Preservation at the level of quantum information is not resurrection. It is stricter and colder. It says only that the difference between what happened and what did not happen remains present in the final state of reality. That may be all physics can promise. And perhaps it is enough. Because if the page curve is right, if the radiation ultimately purifies, if the islands are pointing toward a deeper accounting, then the black hole has not broken the universe's memory. It has forced that memory into a shape no ordinary imagination can hold. It has shown that information can survive by becoming non-local, relational, encoded in correlations so fine that every simple picture fails. The black hole does not hand history back. It dissolves history into structure. And the structure may still be exact. Reality may not be made of things first. That is the final destabilization black holes press toward. Not because matter is unreal, not because stars and bodies and stones are hallucinations, but because matter may not be the deepest way the universe keeps account of itself. Objects are what reality looks like after a more severe structure has become stable enough for human senses to survive inside it. A stone feels primary. It resists the hand. It falls. It breaks a window. It waits in a field for centuries with the patience of something that seems to need no explanation beyond itself. But the stone is already a compromise between deeper languages. Its solidity is electromagnetic repulsion and quantum exclusion. Its weight is curved space-time and inertia. Its temperature is molecular motion. Its shape is an arrangement maintained against time by forces the eye never sees. The stone is real. But it is not fundamental in the way the hand believes. A black hole pushes this lesson past comfort. It does not simply say that matter is made of smaller parts. That old revelation still leaves the world familiar. Molecules become atoms. Atoms become nuclei and electrons. Nuclei become quarks and gluons. The story descends through smaller things, but still feels like a story about things. The mind can follow it because it imagines nature as a set of nested objects. each deeper layer made from smaller pieces hiding inside the last. Black holes suggest a more unsettling descent. The deepest layer may not be smaller objects. It may be distinction itself. Information, in the physical sense, is the preservation of difference. This state rather than that state, this arrangement rather than another, this history rather than an indistinguishable alternative. A universe that preserves information is not merely keeping a record for observers, it is maintaining the separations that allow events to be meaningfully connected across time. If those separations vanish, law itself becomes less sharp. That is why the black hole feels so severe. It appears to take everything rich and particular, a star with layers, turbulence, magnetic fields, nuclear history, perhaps planets and dust, and the remnants of ancient explosions, and reduce the exterior description to a few numbers: mass, charge, spin. Then quantum theory says the black hole radiates, then evaporation threatens to leave behind only a field of outgoing quanta. The entire drama becomes an argument over whether the original distinctions survive the journey, not the matter.
The distinctions.
This is the reversal. Matter can be crushed, transformed, ionized, fused, torn into plasma, folded into fields, converted into radiation. Form can die, chemistry can die, structure can die. But if quantum mechanics is right in its deepest insistence, the distinctions do not simply die. They migrate into the complete state. They become correlation, phase, entanglement, subtle relation. They may stop resembling what they came from. They may be useless to every observer. But they remain part of the world's exact accounting. Reality may not be made of things first. It may be made of differences that cannot be erased. That sentence is not a slogan. It is the pressure created by the paradox. A black hole tests whether the universe values distinguishability more deeply than it values the familiar shape of space. If preserving information requires the horizon to be less absolute, then the horizon must change. If preserving information requires the interior to be encoded on a boundary, then volume must lose its innocence. If preserving information requires radiation to contain an invisible architecture of correlations, then heat must become less simple. If preserving information requires space-time itself to emerge from entanglement, then space cannot remain the bottom layer. Everything bends around the demand that the difference survive. This is why the information paradox becomes more frightening as it becomes more precise. The old fear was visual, a dark object, a cosmic drain, a place where light fails. The mature fear is structural, the possibility that what we call reality is an enormous system of constraints designed, somehow, to keep distinctions from being annihilated, even when geometry seems to forbid their return. The black hole is not an exception to order. It may be the place where order reveals how strict it is. There is something almost merciless in that thought. Human beings care about forms. We care about the body, the face, the voice, the letter, the room, the planet underfoot. We want preservation to mean restoration. If a thing is saved, we want it to remain recognizable. But physics offers a colder preservation. It may save only the information, only the exact difference, only the state's place in the total evolution. The form can be lost forever, while the law remains satisfied. The universe may remember without mourning. That is not comfort. It is clarity with no human softness in it. A star that becomes a black hole is not restored by information preservation. Its light does not return to its surface. Its planets do not regain their orbits. Its collapsing core does not unfold into the sky again. If its information survives, it survives as something almost unimaginably abstract, encoded in correlations, boundary degrees of freedom, or a final radiation state spread across the future. The biography remains in principle, but not as biography. The record is exact. The world is gone. This distinction is where the emotional pressure deepens. We began by asking whether black holes destroy information, but the question now has a more unsettling answer. Perhaps they do not destroy information precisely because information is more fundamental than the objects we first cared about. The universe may preserve the distinction between one lost world and another, while allowing both worlds to vanish as worlds. That is severe beauty. Not sentimental beauty, not the beauty of rescue, the beauty of a law that refuses to break even when every image we understand has been destroyed. A black hole may be the universe's harshest proof that recognizable existence is not the same as physical persistence. This also changes what the horizon means. It is no longer only a boundary of no return. It is a surface where two descriptions collide. The classical description, in which information falls inward and disappears from the outside account, and the quantum description, in which the total state must remain rich enough to distinguish every allowed history. The horizon becomes the stress line between appearance and accounting. From outside, the black hole looks simple. From the deeper theory, that simplicity must be an encoded complexity. The calm exterior is therefore not emptiness, it is compression. The horizon's area is not merely geometry, it is the visible face of hidden capacity. The radiation is not merely heat, it may be the slow release of a scrambled record. The darkness is not merely absence, it is the failure of ordinary vision to see where reality has placed its ledger. And once that is understood, the phrase "missing from black holes" changes meaning one last time. The missing thing was never sitting inside them like a core. It was never waiting behind the horizon as a secret object. It was missing from our picture. We tried to describe black holes with geometry alone, then with quantum fields on that geometry, then with thermodynamics added like a warning label. Each picture captured something true. None could carry the whole burden. The missing thing was the deeper accounting. The law beneath the image. The insistence that distinction cannot simply be erased. If that insistence is right, then black holes are not where reality becomes vague. They are where reality becomes too exact for our inherited categories. They expose the weakness of thinking in objects when the deeper world may think in states. They expose the weakness of thinking in places when the deeper world may organize itself through relations. They expose the weakness of thinking that disappearance means non-existence. A black hole does not merely swallow matter. It separates what humans mean by gone from what physics means by lost. And the two are not the same. Return now to the machine underground. Not because it solved the mystery. Because it teaches the shape of the mystery by failing to give us the easy version. The Large Hadron Collider is, in one sense, an instrument of collision. It accelerates protons, bends them through a buried ring, and lets them meet at energies high enough to break open the familiar. But in a deeper sense, it is an instrument of refusal. It refuses to let theories remain vague. It refuses to let speculation float without consequence. It asks nature for a signature, and if the signature does not appear, the absence becomes part of knowledge. This is what happened with microscopic black holes. In certain theoretical models, especially those involving extraspatial dimensions, gravity might become strong at much smaller scales than expected. If so, proton collisions at extreme energy could briefly create tiny black holes that would decay almost instantly into many particles. The detectors would not see a small dark sphere sitting there. They would see a pattern. Energetic sprays, high multiplicity events, decay signatures, a statistical excess above known processes. The detectors waited for those patterns. They did not find them. That statement is not a disappointment in the shallow sense. Science is not only a machine for confirming dramatic ideas, it is also a machine for narrowing the possible. A non-detection, if the search is careful, can cut away regions of theory. It can say, if microscopic black holes exist in this model, they do not appear below these energy scales, with these assumptions, in these data. The result is not the final answer to quantum gravity, but it is a boundary, a disciplined absence. Sometimes the most important discovery is the shape of the absence. The viral version wants something else. It wants CERN to have found the missing thing. It wants the detector to catch a tiny black hole in the act of confession. It wants an announcement, a particle, a breakthrough with sharp edges. It wants the abyss to fit inside a headline. But the real story is more severe. The missing thing was never going to be found as a glowing shard in a collision event. The black hole information problem is not a missing particle problem. It is not like searching for the Higgs boson, where a field predicts a particle and the detector can find its statistical footprint. It is a missing consistency problem, a missing bridge, a failure of our deepest languages to speak together without contradiction. CERN can test pieces of the boundary. It can search for new particles, extra dimensions, supersymmetric partners, microscopic black holes, deviations from the standard model. It can reveal where speculative theories survive and where they begin to die. It can create conditions where the quantum world becomes violent enough to expose hidden structure. But it cannot, by itself, make an astrophysical event horizon evaporate and hand back its information in a measurable form. The scale is wrong. The time scale is wrong. The problem is deeper than the detector. That does not make CERN irrelevant. It makes CERN honest. Its power lies precisely in the fact that it brings theory into contact with refusal. It says, if your imagined world affects proton collisions, show yourself here. If extra dimensions lower the true gravitational scale, leave a trace. If microscopic black holes can form at accessible energies, let the debris announce them. When nature answers with silence, the silence is not empty. It is structured. This is how the opening image changes. At first, the collider looked like a possible doorway into black holes, a human-built ring beneath the Earth, pressing energy into tiny regions, trying to make gravity reveal its quantum face. The image was dramatic because it seemed almost forbidden, a civilization attempting, in miniature, to touch the same physics that governs collapsed stars. But after the descent through information, entropy, horizons, radiation, holography, and the limits of intuition, the collider looks different. It is not a doorway to the secret itself. It is a lantern held at the edge of a larger darkness. The black holes that matter most to the paradox may be far beyond the reach of any machine. A stellar black hole's Hawking temperature is too cold, its evaporation time too immense, its information recovery too subtle. The radiation that might eventually carry the record is weaker than the universe's background glow for ordinary astrophysical black holes. No experiment now can gather the final whisper of a dying cosmic horizon and reconstruct the state that formed it. But the lack of access is not the same as lack of meaning. Physics often advances by pressure from many sides. Astronomers observe real black holes through their gravitational influence, accretion disks, jets, stellar orbits, and gravitational waves from mergers. Theorists test quantum gravity in mathematical models, where black hole evaporation can be studied more cleanly. Particle physicists search for high-energy signs that gravity or space-time has hidden structure. Quantum information scientists sharpen the language of entanglement, entropy, error correction, and reconstruction. No single path owns the mystery. Each path tightens the net. CERN's role is not to declare that the missing thing has been found. Its role is to remind us that reality does not owe our theories a spectacle. That reminder matters. The black hole information problem is so conceptually intoxicating that it can easily float away from discipline. Words like holography, information, horizon, and quantum gravity can become a fog of almost mysticism if they are not held against what physics actually knows. CERN is one of the anchors. Its detectors do not care how elegant a speculation sounds. They care whether events appear. And in the case of microscopic black holes, they have not. So the story returns to humility, but not to emptiness. The absence of microscopic black holes at the LHC does not remove the information paradox. It removes one easy fantasy of access. It tells us that the bridge between quantum mechanics and gravity is not waiting at the first dramatic energy scale we hoped for, at least not in the searched forms. The paradox remains where it has always been, in the conflict between a horizon that hides, radiation that evaporates, and quantum theory that refuses erasure. That remaining conflict is larger than a discovery announcement. It is the contour of a future theory. One day, perhaps, quantum gravity will make the accounting exact. It may show how information returns through correlations in Hawking radiation. It may show how the interior is reconstructed from boundary data. It may show that space-time emerges from quantum entanglement in a way that makes the paradox dissolve. It may show that some cherished assumption must be surrendered. The answer may be elegant, or brutal, or almost impossible to translate into ordinary language. But it will have to satisfy the same severe demand. Where's the record? Not metaphorically, not spiritually, not in the comforting sense that something matters because it once existed, physically, in the final state, in the correlations, in the degrees of freedom, in the mathematical structure that lets the universe remain accountable to itself. That is the true bridge the title reaches for and misses. CERN has not found the one thing missing from black holes. But CERN helps define what such a discovery would have to mean. It would not be a headline saying darkness has been solved. It would be evidence, or theory tied tightly enough to evidence, showing how gravity preserves quantum information without lying about horizons, evaporation, entropy, or locality. It would be a way for the universe to keep its memory while still producing the black holes we observe. The machine underground remains patient. Protons circle, magnets hold them. Detectors wait in cathedral darkness for collisions that last less than a trillionth of a blink. Most events are ordinary by the standards of high-energy physics. A few are rare. Some are searched for over years. Many hoped-for signatures never arrive. But absence, when measured carefully, is not nothing. It is reality drawing a line. And beyond that line, the black hole remains, not as a monster caught in a machine, but as a question too large to fit inside one. The missing thing was never in the detector alone. It was in the space between our theories, in the unfinished grammar of gravity and quantum mechanics, in the demand that the world explain how anything can fall beyond return without making the past less real. The collider did not open the abyss. It showed us where the abyss was not. The black hole is quiet again. Not because the question has ended, but because silence means something different now. At first, the darkness looked like absence, a place where light fails, a gravitational wound cut into the sky, a final mouth for stars, planets, dust, and every fragile arrangement that falls too close. The imagination sees it as a cosmic eraser, because that is what darkness has always meant to the eye. No image, no signal, no return. But the eye was never the authority. A black hole is not terrifying because it is dark. Darkness is only the surface of the problem. The deeper terror is that the darkness must still obey law. It must have entropy. It must have temperature. It must radiate. It must either preserve information or force physics to admit that preservation was never absolute. The horizon is not merely a place where seeing stops. It is where the universe has to defend the difference between hidden and gone. That difference now carries the entire weight of the story. A thing can be hidden and still exist in the accounting. A thing can be scattered and still remain present in the correlations of the world. A thing can be burned, broken, dissolved, mixed into heat, and lost to every practical observer, while the complete state still preserves the distinction between what happened and what did not. But gone is colder. Gone means no record, no distinction, no final state rich enough to know which beginning was real. Gone means many pasts compressed into the same future, with nothing left anywhere to tell them apart. That is not ordinary loss. It is the severing of the thread by which law connects one moment to the next. Black holes brought that possibility into physics with almost cruel elegance. They did not do it with spectacle. They did it with simplicity. Mass, charge, spin, a horizon, a temperature, a faint radiation, a lifetime. These sparse ingredients were enough to place the foundations under pressure. The star collapses. The horizon forms. The details vanish from outside view. The black hole slowly radiates. The radiation appears thermal. The object fades. The archive, if it was only inside, has no obvious place left to remain. The question becomes impossible to soften. What happened to the information? Not the image, not the body, not the star as a star. Those can be destroyed without violating the deeper demand. What must survive is harsher and less human, the exact physical distinction between one possible state and another. The universe does not have to return the world in a recognizable form. It does not have to restore the fallen book, relight the collapsed star, or rebuild the body from its last atoms. It only has to avoid confusing one reality with another. That is the severe promise quantum mechanics seems to make. And if black holes honor that promise, they do so in a way that strips comfort from preservation. The information may not sit anywhere simple. It may not be stored in a familiar interior. It may not be carried by any single escaping particle. It may be spread across correlations in Hawking radiation, encoded in relationships so fine that no observer could realistically gather or decode them. It may require a holographic description, where boundaries carry what volumes seem to contain. It may require space-time itself to be less fundamental than the informational structure beneath it. The universe may remember in a language no creature can read. That is not a failure of memory. It is a failure of our scale. We wanted information to mean a recoverable message. Physics may mean only that the final state remains exact. We wanted survival to mean restoration. Physics may mean distinguishability. We wanted the black hole either to destroy or to return. The deeper answer may be stranger. It transforms, scrambles, encodes, and disperses without letting the underlying distinction become nothing. A preserved record is not a resurrected world. This is why the ending cannot be triumphant. Even if information is preserved, the black hole remains devastating. The star is gone as a star. The falling observer does not come back. The original form does not reappear out of the radiation, like a film running backward. Preservation at the level of fundamental law is not tenderness. It is accountability. The universe may keep the books while allowing every page we care about to burn beyond recognition. That is the cold elegance. The law may be faithful where reality is merciless. The horizon, once imagined as a border around darkness, becomes something sharper, a stress mark in our understanding. It shows where general relativity, quantum mechanics, and thermodynamics each speak with authority, and yet cannot all remain naive. It shows that an interior may not be independent from its boundary in the way ordinary space suggests. It shows that heat may carry a hidden exactness. It shows that emptiness around a black hole is not empty enough to stay silent. It shows that what we call a place may be less fundamental than the relations that allow place to appear. The black hole has changed from an object into an accusation. It asks physics to name what is real enough to be preserved. Matter is not enough. Matter changes. Forms dissolve. Stars burn themselves into heavier elements. Galaxies collide and forget their old shapes. Bodies live briefly and return to chemistry. The visible world is a theater of rearrangement. If the deep law cares about anything with absolute severity, it may not be the object. It may be the state, the distinction, the information. That thought does not make reality gentler. It makes it stranger than destruction. Because a universe built around information is not a universe built around human meaning. It does not promise that what matters to us remains whole. It promises, perhaps, that nothing physically distinct is allowed to become indistinguishable in the final accounting. It may preserve the difference between two vanished stars, while caring nothing for the stars as stars. It may remember everything without resembling memory at all. Return, then, to the first image. A machine underground, protons moving through darkness, detectors waiting for impossible signatures. A headline claiming that CERN found the one thing missing from black holes. The literal claim dissolves. No microscopic black hole confessed itself in the data. No detector caught the final answer to quantum gravity. No experiment has watched an astrophysical black hole evaporate and read the information in its final glow. And still, the title pointed toward a wound. The missing thing was not a particle. It was not an object. It was not a secret substance hidden behind the horizon. It was the missing bridge between the way gravity draws boundaries and the way quantum mechanics preserves distinctions. It was the missing grammar that can say how a black hole may vanish without making the past less real. It was the missing account of how reality keeps its records when space and time themselves no longer seem trustworthy enough to hold them. The black hole waits at the edge of that account. No flames are required, no cosmic roar, no theatrical violence, just a surface that is not a surface, a darkness that is not empty, a radiation that may not be random, a silence dense with unfinished law. Somewhere beyond the reach of direct vision, a black hole may be slowly giving itself away, one quantum at a time. To any eye, it is almost nothing. To the deeper accounting, it may be a final ledger written across the future. Not a story, not a confession, not a memory in any human sense. A distinction that refuses to die. The darkness was never empty. It was where reality hid the question of whether it can forget.